their size or orientation. So this is just an example of a transformation. So we have an original figure of triangle with the center at its origin. We are showing a rotation. As you can see, it kind of oriented like the triangle got oriented in a direction, and the other thing and the next image shows a translation where we shifted the triangle from origin to some other point. So this is basically an example of showing a 2D transformation. So yeah, I'd like to start with the first topic on the transformation is translation. So translation is a movement of an object from one position to another in a straight line movement. Basically, in the previous figure, translation is a movement from figure 2 to figure 3. So translation happens when every point in the of a position gets moved gets moved with a distance tx and ty, which are predefined by the user. So predefined by the user. If we are trying to translate a point xy to x1 comma y1, we do it using the equations x1 equal to x plus tx, y1 equal to y plus ty. Here's an example of a triangle showing a translation of x being plus 7, tx being plus 7, and ty being minus 4, ty being minus 5. As you can see, like we are shifting the points p, q, r to p dash, q dash, r dash respectively in a straight motion, and the distances will be same for all. And we yeah in a famous way for showing transformations is through matrix notation. When we go for much complex transformations and all for visual representation and also for easier understanding purposes, matrix notation is what used in wide range. So the matrix for the general equations are x dash equal to x plus x and y dash equal to y plus ty. We can represent them in matrix equations as p dash equal to p plus t, where we are assuming p dash is a output matrix, p is the input matrix, and t is the translation matrix, as shown in the as I've shown in the slide. Yeah, so rotation is another kind of transformation available for the user. Rotation is basically changing the angle of the object with respect to a point of rotation. When we are trying to perform the rotation operation, we need to have specify the angle of rotation, that is how much degrees we are trying to rotate, and we also need to mention the rotation point. We also need to mention do we want to do the rotation in clockwise direction or anti-clockwise direction. In the figure here, like the one I'm pointing is the starting point and the other is the ending point. We are showing the a rotation of counterclockwise, anti-clockwise or counterclockwise, and in the second figure we are again showing the backwards rotation to clockwise. One second. Yeah, clockwise. So yeah, rotation in general can happen with respect to origin, or with for a two-dimensional space. Rotation can happen with respect to origin or with respect to an anonymous point. Anonymous point is what is used in general, but we start with origin as it's easier, and we use origin as a reference to calculate any point, any arbitrary point. So we'll be starting I'll start in explain with the origin as the center. So when we are considering origin as a rotation point, we will let's assume the new points as x dash as y dash, and all points as x comma y, and we are assuming that the degrees we are rotated is theta degrees. So like as shown in the figure, like we can see that x comma y is the point o, and x dash comma y dash is point o dash. Uh, Basically we can use trigonometric equations to get o as x o as if we are considering this as r. If we consider the if we draw a circle like this, we can consider the radius as r. Then we get the coordinates of o as r cos theta comma r sin theta, and we get o dash for r cos theta plus phi comma r sin theta plus phi. When we use some of the deeper standard trigonometric calculations, we can derive the equations to in the form of x dash as x cos theta minus y sin theta and y dash as x sin theta plus y cos theta. As we have seen, like when we moved anti-clockwise, the x has went backwards and y has shifted upwards. We can consider this as the why we got plus and minus symbols. And if we're doing a clockwise directions, we simply substitute theta with minus theta, which we are gonna get as something else like x cos theta minus uh, sorry. And for the matrix notation for rotation, like it is a bit more complicated compared to translation, and we will be using multiplication, matrix multiplication instead of addition in this case. The matrix form for the equations, equation shown here can be written as this format in the given below, and we can consider it as p dash equal to p dot r, p matrix multiplication of p and r.
Okay, quick question.
Yes, sir.
Yeah, let's say you take a rotation, say 37.69 degrees
Yes.
in let's say counterclockwise.
Sure.
Then you're going to take the rotation back 37.69 degrees clockwise. Will you get the same point?
No, like we need to go shift the position towards anti-clockwise. So like if we move in clockwise direction, we're gonna do an opposite rotation.
No, what I mean is you go one direction and just do the inverse of it. Okay.
Yes, we can get it.
You get the same point.
Yes, if we are doing inverse with respect to the original, like if we are rotating from O to somewhere below, and if we do inverse with the line respect to origin and O, then we get the same. Then we get the intended point.
Okay, so let's say I rotate from O to O prime,
Okay.
and then from O prime back to O, and
Okay.
get the distance of the original O and the one that I just got by rotating back. You think the distance is going to be 0?
Uh, yeah, the distance. I did not get your point. Like the distance between O to O prime.
No, it's just go from O to O prime and then go back from O prime to, let's say, O double prime, where the
Okay.
O double prime is supposed to be the same as the O.
Okay.
So in floating point arithmetic, are you going to get the same point?
Yes.
I would suggest you try it at home, write the code, and
Uh,
see what kind of error you're going to get when you rotate it back.
Oh, so basically, like we are rotating. Are you saying like we are rotating, let's say 30 degrees from O to O prime and in counterclockwise direction, and rotating back 30 degrees in counter clockwise direction?
Mhm.
Uh,
Right.
and yeah, then shouldn't we be getting the same point? Like since we'll be rotating back the exact distance, so we'll be
Well, you
getting to
get the same point with respect to a certain error, where you're going to get some error. In floating point arithmetic, nothing is precise. So if you rotate, especially with some really uneven numbered angle like
yes,
49,
yeah,
49.12789 and then go back, you're going to get quite a bit of error in that because the
yes,
sine and cosine functions are not precise. These are
yes,
approximations. Even
yes,
if you rotate with 30 degrees plus and 30 degrees minus, you are not going to get the same point. There's going to be some error in the very couple of last digit, but if you rotate with a fairly imprecise angle, you're going to get more and more of an error. Now
yes,
you could do this multiple times, right? You can rotate counterclockwise 4, 5, 10 times and then go back and see what kind of error you're going to have because the error is going to accumulate over
yes,
time, right? So the real
yes.
question is if I do like a 10 rotations one way and 10 rotations back, will I going to have big enough error so they're going to have the 2 points within 2 different pixels?
Yes, we will be getting a error which can be, which will be a bit different from the original point?
Yeah, that could be. If you do it long enough, the error is going to accumulate long enough, and you may not get the original point back. You're
Yes.
going to get a little bit of an error. So these sine and cosine functions are mathematically correct, but when you calculate them, you're not going to get the really accurate results. Let's keep
Okay.
this in mind, right?
Yeah. Yes, doctor.
Okay, let's continue.
Yeah, sure. So as I was saying, like the matrix notation is represent as p dash equal to p matrix multiplication of r, where we are considering r as cos theta sin theta minus sin theta cos theta. It's another sign of matrix notation which we'll be using for rotation. And rotation at arbitrary point. So rotation at arbitrary point is we generally consider it. We generally perform it doing 3 steps. If we are considering the arbitrary point as xp comma yp, like as shown in the figure a here. At first we try to convert we try to translate the entire picture so that the translation point is converted to the origin, like as shown in figure b. We translate the point from xp comma yp to the origin. So one second, we translate the point xp comma yp to the origin. Then later we will be rotating it with respect to origin, as we already have the rotation matrix available, and if we know, if we, and the user will be giving us the degrees with which we need to rotate. So hence we'll be rotating it as similar to rotation about the origin. Once the rotation is done, we will translate the point back to the original position as shown in figure d, which will give us which will give us which will give us the point which was intended when we rotate about an arbitrary point. It's a 3-step process, like I just mentioned it here: translate point center to origin, rotation of x comma y about the origin, and translation of center of rotation back to its original point position. So rotation at arbitrary point is generally has 3 steps, and each step has its own separate notation with own separate matrix notation, with translation point for the first one being a translation matrix, second one being a rotation, and third one again being a translation matrix. It requires 3 steps, and it requires 3 steps. So continuing on, I'll continue with 2D scaling. 2D scaling is another concept which, as I've explained in the previous, as I will try to explain with the construction example. We do scaling, especially when we wanna diminish the image to a certain point, or enlarge the image to a certain point, such that it's more pleasing to the eye, or the details will be more better in a given size rather than the original size of the object. So scaling is done when we try to enlarge the image. While creating scaling, we give 2 factors scaling in scaling the for x direction and y direction, sx in x and sy in y direction. Scaling, there are 2 types of scaling: uniform scaling and non-uniform scaling. Both are similar, except for the case that in uniform scaling we have sx and sy as seem equal. And matrix notation is as shown in below, like x dash y dash equal xy into sx 0 sy. It's also considered as it's also in the form of matrix multiplication: p dash equal to matrix multiplication of s. These are some examples for uniform scaling and non-uniform scaling. Here I'm showing an image of a square which has been enlarged uniformly, so it retains the properties of a square. But it's enlarged in size. And we have another example of non-uniform scaling. Here we are enlarging only in the x direction and not in y direction. As you can see, like the door of the small house frame has become very big, very widened to the point that it's become a rectangle towards the x side rather than at the y side, like where here y was more and here x was more. Like non-uniform scale in non-uniform scaling is used when non-uniform scaling is performed, the properties of the image itself may change. Like here, like it's becoming square to rectangle. A triangle is a equilateral triangle can become something else of triangle, an acute angle triangle, etc. And yeah, the next concept we're gonna be discussing is homogeneous coordinates. So first we're gonna think of why do we need homogeneous coordinates. Like homogeneous coordinates is like just a different way of representation, but why do we need a different way of representation? So to answer this question, we can consider one of the previous scenario which I've explained, by where we did a rotation with an arbitrary point. We have seen that it takes 3 steps, but using homogeneous coordinates we can condense it into one single step. And we can condense it into less steps, generally in one step. So into one step, which will be explained further in the presentation. So basically, to combine homogeneous coordinates are considered as x, y, w for 2 dimension. So basically, a homogeneous coordinate is adding another dimension to the existing dimensional space. By for 2D, we'll be representing it with 3 dimensional space. We like the Euclidean coordinates x, y are represented by x, y, and w. So you to convert Euclidean to homogeneous or homogeneous to Euclidean coordinates, we basically like if we have the homogeneous coordinates as x, y, and w, we can consider the Euclidean coordinates as x by w or y by w, representing the corresponding point in Euclidean coordinates. W is a scaling factor or weight. To convert back to Euclidean coordinates, you simply divide x and y by w. We can see the use of w with the example. Here we can consider the when the w is 3, like the point has been shifted to the red point over here, like with the bigger margin, like 21 and 15. But when with 21 and 15, but when we consider w as 2 or 1, the points shift. But when we change them all back to so we with respect to w, we can get infinite number of homogeneous coordinates, but which all will be representing one one coordinate in Euclidean, will be represented by infinite coordinates in homogeneous. This will this useful in matrix notations and all. So the matrix notation for Euclidean coordinates, for the previously explained for the previously explained transformations or translation is tx and ty are the translation factors in x and y, and we put them in the third row at the last, tx, ty, tx, and will be performing addition operation. And for scaling, it will be at the sx and xy. We will be adding a third one with third row and column with one added at the last at the diagonal matrix. For the rotation also it is similar. The operations which we will be performing for translation, scaling, and rotation remain the same. We will be performing addition for translation, multiplication for both scaling and rotation. Yes, further of the presentation will be continued by my team member Srija.
Okay, thank you so much. It's a very nice and comprehensive introduction. Let's
Thank you, Doctor.
mhm.
Srija, you can take the screen.
I'm sharing my screen. Yeah, now I'm going to continue about the inverse transformations. As I have mentioned about the translation, rotation, and scaling, now we are discussing about the inverse of that. And generally, when we consider a matrix as 1, 0, t of x, when t of x and t of y are the translations, in inverse, we consider it as minus. So, and as on translation, it's just like a shifting of the point. In this context, generally, while dealing with planes, we refer with respect to origin. So translation is mostly used while considering a point changing by its angle or any other scaling things. In rotations, we the overall multiplication matrix would be of cos theta, sin theta, o minus sin theta, cos theta, o 1. In this process, we are going to rotate the plane by certain angle in positive or negative axis depending upon our requirement and the plane's axis. And scaling, it's like diminishing or enlarging an object by a particular factor. A value something less than one is considered something more than one is considered to be enlarging, and something less than one is considered to be diminishing, until and unless a small change doesn't affect the plane as a whole. Uh, then is it possible to do multiple transformations at a time? Yes, the answer is yes. In transformations, when we perform multiple operations, it must be always in a sequential order. And this process of doing multiple transformations at a time is known as a composition or a concatenation of the transformations. And uh, in this process, generally the order of the process matters much. For example, we are first performing scaling and then rotation. That the final output will not be same as like for example, let me take M1 and M2 are the two operations that we are performing, and the final new plane would be P dash. uh, the operation M1 M2 into P is not at all equal to M2 M1 into P. So for a two-dimensional for a two-dimensional plane, for translation, the equation would be in this form. The final coordinates for the translated plane would be, with respect to x coordinates, it will be t1 plus t2, where t1 and t2 are the two different transformations that we have made for a particular plane. And for y-axis, it would be t1 plus t2 with respect to the two operations that we have did. In the same way, while coming to the angles, theta 1 and theta 2 are the two angles that we have rotated the plane to. Then the final overall affected plane would be suffering from the both theta 1 and theta 2 references. And while coming to scaling, as diminishing or enlarging multiplies as we are increasing. So with respect to x-axis, it would be S1 and S2, where S1 and S2 are the scaling factors that we have used, and similarly for the y-axis. Here we can observe an example. As I have previously mentioned, while we are performing any operation on a plane, uh, it's like we need to take the object with reference to the origin and then perform our scaling or any other translation. Here, the image represents this is the original image. Then we have translated the object with respect to origin, and then we have scaled that particular object. Here we can see the image has been enlarged, and then we have rotated it by 90 degrees. Uh, in this form, the final output would be in this format. And again, we need to convert, like we need to make this image shift to the original position using the translation again. So the overall matrices we will be of this form. We can see first we have performed translation here. So for translation, the matrix would be in this form. Then scaling. This is the matrix for the scaling after translation. Sorry. This is rotation. The final matrix for the rotation, when we are rotating, where we have rotated the image in a clockwise direction, the final resultant matrix will be of this form. So, as I've mentioned, when we are doing multiple translations, the overall effect would be the product of all the transformations we have made. And for an instance, let us consider this as M1 transformation, M2, and M3 transformation. So, M1 into M2 into M3 is not at all equal to M1 into M3 into M2. So, next, coming to rotation of rotation with respect to an arbitrary rotation on an arbitrary plane. First, this is the original position of the object. The sequence of steps would be, first we need to take the original position of the object, then make it centered with the origin, and then rotate it or scale it or any other transformation with respect to the origin, and then translate the object to its original position. So here we can observe in first image, the object is in the positive coordinate. Then it has been transferred with respect to the origin. And then the rotation, here we can observe the difference in the angle, the base of the triangle. So it is being rotated with some angle. Here it is 90 degrees when we see the both images. And then we are shifting the image to its original position. So as in the original position, this is the new position and the new rotated angle for the object. So mathematically, we can represent this as in this form. So first, the translation was with respect was shifted. The plane was shifted to the origin. So this would be the matrix where x and y are the points we have shifted to. And then this is the matrix for the rotation of the image. And then the translation back to the original position would be this. So final matrix can be represented as of this form, where first we have translated, rotated, and then translated the whole plane. And the resultant matrix would be of this form, where the first row has the effect of first translation, then rotation would affect with all the thetas, and then the second re-referenced planes would be with xr and yr here. Then now coming to scaling with respect to the arbitrary point. So here also, as the previous rotation, the original position, this is the original position of the object. Then we need to move it to the origin or the translation towards the origin. And then we have enlarged or scaled the object. Here we have enlarged it, or we can generally diminish also. Then the object is moved to its original position or to original position, and this shows the final overall affected plane. Again, coming to the mathematical representation, this would be the mathematical representation for that, where first one is the translation for the origin. This is for enlarging with a factor of s of x and s of y on the particular coordinates, and then making the object back to its original or arbitrary positions. And this would be the final matrix, where first one is the translation, then scaling, again the translation in opposite direction. Now Pujita will continue the presentation.
Very good.
Good afternoon. Is my screen shared, Professor?
Yes, we could see it. Put it in. There you go. Very good.
Yeah. So I'm going to cover scaling of an object in specified perpendicular directions, and if these transformations are relevant, order of these transformations are relevant or not, and computational efficiency of using homogeneous coordinates, and what are rigid motions and rotation using orthogonal vectors. And also we're going to see about reflections transformation and reflections with respect to x and y axis and the diagonals. So coming to scaling in a specified perpendicular direction involves changing the size of an object along an axis that is perpendicular to a given direction. So the process would be, first we need to rotate the object so that the directions for S1 and S2 coincide with X and Y axis. And we need to scale the object with respect to the origin using S1 and S2. And later we need to rotate back the object to its original orientation. So here we can see the composite matrix resulting from the product of these three transformations. So here we can see this is the matrix transformation resulting to the rotation of S1 to the x-axis. And this is the scaling matrix, and this is the rotating back to the original orientation. So here is the R of theta and S of S1, S2 and R inverse. So this is the resultant matrix. And here we can see an example. We can transform square into a parallelogram by stretching the diagonal. Here we follow these three steps. that says rotate the square until the diagonal aligns with y-axis. So first we need to rotate the square until the diagonal aligns with the y-axis, and then scale the square by using first scaling metric as 1 and second scaling metric as 2. And we need to rotate back to the original position, which results a parallelogram as shown in the image. So if we see like if the order of transformations are relevant or not. So if we take like in the homogeneous coordinates, it simplifies the representation of transformations using matrices. So we can represent translation, rotation, scaling, and shearing different transformation operations in a consistent manner. So when we multiply a point represented in homogeneous coordinates by such matrix, the computations can be more efficient due to the regular structure of the matrix. So here, the multiplication of matrices, we know the multiplication of matrices obeys associate law. For example, if there are 3 matrices saying M1, M2, and M3, then the product of M3, M2, M1 is equals to product of M3, M2, M1, which is equals to the product of M3 and M2 and M1. In a composite transformation, the order of individual transformations is important. For example, if we first rotate, then scale, then translate an object, we get a different result than if we first translate, then rotate, and then scale an object. So, for composite matrix, depending on the order of transformation, we can multiply either from left to right or right to left. But we need to first fix the order of transformations. And when performing the matrix multiplications, we need to consider that matrix multiplications are not cumulative, which means the product of M2 and M1 is not equals to M1 and M2. But in some special cases, transformations are cumulative. Some of those cases are, in the first case, the sequence of transformations that are of the same kind, like 2 successive translations or 2 successive rotations and 2 successive scalings. This will result in the same final position of an object. So if we take 2 successive translations, we can perform in any order. And in the second case, rotation and uniform scaling are also cumulative. Like first we can scale the object and then rotate the object, or first we can rotate the object and perform uniform scaling. Both ways it results the same position of the object in the final. So in the third case, translation and rotation of an object are also cumulative. As shown in the image here, first the original position of the object is this, and when we first we are performing the translation, which results in the second image, and then if we rotate it, it gives the final position as like this.
Very
Or
good.
if
So,
yeah.
excuse me. So we got here a lot of transformation, translation, rotation, scaling, shear, and we can introduce a bunch more. Now, how do we know if we are doing the right combinations? I want to do a lot of different things: translate, rotate, and so on. How does the system know that the order is going to be important or not important? Or is just going to find out when I do it twice and in a different order? Let's say I'm doing interactive graphics, and in one way, first translate, rotate, and scale. Another way, first scale, translate, rotate. I'm not going to get the right answer. How do I get around this? How do I avoid mixing up the order of transformations? Any ideas?
We can plan it out.
Anybody can answer the question. Yeah, go ahead.
We can plan it out, like plan the actions of what needs to be done at the start before, rather than starting it at the planning it out.
That's one idea. We can plan the transformations. When you do interactive graphics, you don't really know ahead of the time what you want to do. You just design the object and say, I'm going to have to move it over here. Okay, let me rotate a little bit and put it in place by scaling it. Wrong way. Never mind. I'm going to do it the other way around. And it's just not going to come out the right way. Is there a way of guaranteeing that no matter what I do, I'm going to end up with the final result?
I would say like we know the two basic rules like the rotation and uniform scaling are cumulative and the translation and rotation of an object are cumulative. So keeping that in mind, we can maybe choose the transformation order.
Yeah, that may be an idea to educate the user as to how the orders are not the same if the user wants to repeatedly do the various transformations. Or, as was suggested, we can have a plan. As you do the rotation and translation, you can see what kind of transformations have been done in a history tree or a history file, so that the user can essentially do it exactly in the same order. And if the user doesn't want to do it in the same order because first he has to scale, fit into a certain piece, then the user understands that you don't get the same answer. So some kind of feedback is necessary, otherwise
Yeah.
you're gonna be in trouble, right?
Yeah.
Okay, let's continue.
Yeah. So here, by this we can understand that translation and rotation of an object are also cumulative. And coming to the computational efficiency of using homogeneous coordinates. So we know that homogeneous coordinates simplify the representation transformation using matrices. So here we can say representation of a two-dimensional coordinate position in a three-element representation is called homogeneous coordinate. So in two-dimensional transformation with any combination of translation, rotation, or scaling can be represented as this way. See, so here the four elements, uh, those are RSJK, like RSXX, RSXY, RSYX, RSYY, the multiplicative rotation scaling transformations. And elements TRSX and TRSY are the combination of translation, rotation, and scaling parameters. So if the object is to be scaled, rotate, and translated, then the values for the composite transformation matrix are described as this form. So the translation parameter and rotation parameter and scaling parameter. So the individual transformations has to be done each transformation at a time and require more steps. So we introduce homogeneous coordinates where when we multiply a point represented in homogeneous coordinates by such matrix, the computations can be more efficient due to regular structure of the matrix, and homogeneous coordinates simplify the concatenation of multiple transformations. So the computational efficiency becomes an important consideration in rotational transformations as the rotational transformations contain more trigonometric evaluations. Uh, like for small angles, cos theta is approximately equal to 1 and sine theta value is very close to the theta in radians. So our computations get simpler, and composite transformations often involve inverse matrices, which can be generated with simple procedures like for a translation matrix, we can find inverse matrix by changing the sign of the translation distance. And for rotational transformation, we can find inverse matrix by matrix transpose or by changing the sign of the sign terms. This way, in summary, we can say they simplify many mathematical operations and make it easier to perform transformations. Coming to rigid motions. Rigid motions change the position or orientation of the object without changing the size or shape. So, translation and rotation transformations to the object are examples of rigid motion. The general form of two-dimensional rigid motion transformation matrix can be represented this way. Here, R, JK terms are the rotation terms. These R, JK terms are the rotation terms, and PRX and PRY are the translational and rotational terms. Sometimes this rigid body transformation in a coordinate system is referred as rigid motion transformation. And the important property of this matrix is that the upper left 2 by 2 matrix is an orthogonal matrix. That this matrix is an orthogonal matrix. And if we consider elements in each row, that is Rxx and Rxy and Ryx and Ryy as a vector, then they form an orthogonal vector set. That is, each vector has unit length and vectors are perpendicular. That is, dot product is 0 as represented here. And when these unit vectors are transformed by rotation submatrix, then the vector Rx, Rxy is converted to unit vector along x-axis, and the vector Ryx, Ryy is converted to unit vector along y-axis of the coordinate system. And that can be represented as shown here. If the rigid body transformation is done by first rotating the object at an angle theta about a pivot point x or y r, and then translating the object will be represented like this. So this is the translation parameter, and this is the rotational parameter, and the resultant matrix would look like this. Here, the orthogonal unit vectors in upper left 2 by 2 matrix are cos theta minus sine theta and sine theta cos theta. So it can be represented like this. And coming to reflections, reflections are one of the transformations. A reflection can be stated as folding or flipping an object over the line of reflection. So the original object is usually called as pre-image, and the reflected image is called as the image, and we usually represent something like this. An object and its reflection have the same shape and size, but the figures face in opposite directions. Relative to an axis of reflection, here we can see the object got rotated by an angle of 180 degrees around the axis of reflection. Axis can be in the xy plane or perpendicular to the xy plane as shown here. And coming to the reflections with respect to x-axis, this transformation involves flipping an object over the x-axis. So here we can see this image got flipped with respect to the x-axis, and the x-coordinate here, if we observe, the x-coordinate of each point remains the same, but the sign of the y-coordinate changes. If we see in this case reflections with respect to y-axis, this transformation involves flipping an object over the y-axis. So here we can see this image got reflected with respect to the y-axis, and the y-coordinate remains the same, but the sign of the x-coordinate changes. Coming to reflections with respect to diagonals, here there are two cases: reflections with respect to the diagonal y equals to x, and reflection with respect to the diagonal y equals to minus x. So in the first case, this transformation involves flipping an object over the line y equals to x. So points with coordinates a comma b will swap places with points b comma a. In this case, in the second case, when we are transforming with respect to the diagonal y equals to minus x, the object gets flipped with respect to the y equals to minus x. And the points with coordinates a comma b will swap places with points minus b comma a. So to simplify this, we can use these following simple rules to do different types of reflections.
Hi, this is Sai Krishna, and today I'm going to continue with the previous whatever way my teammates has been done with their topics. So coming to my topic, the reflections with respect to an attribute axis. After the diagonal axis, now I'm continuing with the attribute axis, which is an reflection axis will be a y is equal to mx plus c. Here you can see the steps for the following steps. Translating the line from the origin, like from the attribute line to origin, it's gonna be translated to here, and then it's gonna be rotated to the origin to the minus theta, so it's gonna be rotated towards this, And the reflection matrix, it's going to be reflect the matrix of what we have been in our original position. So after that, the rotation going to be taken into the reverse to the minus theta, as we seen in the following image here. Translate the line back into the arbitrary, which is an original position to the previous original position. So by final matrix will be a t is equal to translate into reflection into reverse reflection into a translate line back to the orbitary. And now it's a shear. The shear is a transformation that slants the shape of the object is called as shear transformations. A transformation in which all points along given a line L remains fixed while other points are shifted parallelly to the L by distance proportional the perpendicular distance from L. You're gonna see these pictures on the next slide. The shearing plan figures does not change its area but changes its only shape. The shear can also generalized in the three dimension in which planes are translated instead of lines. There are two shears transformation. One is X shear and Y shear. One shifts X coordinate value, another shift Y coordinate values. However, in both cases, only one coordinate changes its coordinates, another preserves its value. Shearing is also termed as a squeak. And and distorts the shape of the object, commonly used to shift X and Y values. In any real world can be used as a negative number shift to the left. Coordinate positions are shifted proportionally to the perpendicular distance from the reference line. So here you can see the images over there, which has been shifted to the perpendicularly towards the x value side. You can see the equation x1 is equal to x plus shear xy. You can see here the matrix of shear x, which is gonna be like 3 by 3 into matrix, and these the values for the y coordinate for y axis. So the shear how it's going to be performed here. So you can see the matrix of the y axis coordinates and can be expressed as a sequence of basic transformation scales along the diagonal with the shear maintain the length and orientation parallel to the references here in the image. Shifts are equivalently to translations. And raster methods. Alternative methods for performing 2D transformations stores information as a color pattern in the form buffer. Functions that work on a pixel area for the raster operation. Moving a block is called as a block transfer, like is also called as a pixel it and a bit it. And it doesn't need any arithmetic operation to perform this. Here you can see the image here which has been shifted from here to object to the transformation. Then coming to next slide, the raster methods, then it gonna be take 90 degrees rotation, simply rearrange the elements in the pixel array, reversing the pixel value in each row, then swapping the column and rows rotation 90 counterclockwise. Okay, here you can see that the matrix with 4 into 3, if it is rotated into 90 degrees to comes into 3 into 4, and it's again rotation into 180 degrees, so it comes in the rows and columns has been arranged in 180 degrees as the matrix is 4 into 3. And coming to next slide, the rest rotation that's aren't multiplies 90 degrees need extra processing. Destination pixels are mapped onto the rotation area. Calculate the amount of overlap and average the color of the overlap sources pixel. The weighted by percentage of area overlap could use an anti-aliasing, and the scaling is also done similarly. The reflection reverse rows and column value and combined translations. Shear shift area value position also rows and the columns. The next topic is 3D shearing. The transformation will modify the shapes of the object. This also useful the prospective projection. Here you can see the image. You can see the image in two different ways, like in the two different perspectives. When an object viewed from the different direction and the different distance, the appearance of the object will be a different. Such view is called as prospective view. The matrix of the representing of 3D sharing in the prospective view is here. The matrix of shear 3D is equals to is the matrix 4 into 4 is the really based on the shear. And next topic gonna continue as my friends gonna continue in my team. Thank you.
Yeah, good afternoon, everyone. Today I'm going to present about transformation between coordinate systems, and later on I'm going to talk about 3D transformations. So coming to transformation between coordinate systems, generally computer graphic applications involve various coordinate systems. Transforming coordinates between different coordinate systems, such as converting world coordinates to pixel coordinates. Modifying the camera or viewer's position and orientation to change the perspective or view of a 3D scene. So a transformation between coordinate systems are very essential for computer graphic applications. In computer graphics, coordinate system transformations are the backbone of creating visually appealing and interactive digital experiences. These transformations empower us to position and animate objects, seamlessly switch between different perspectives, and manage complex scenes. Whether it's aligning elements on a screen, animating objects smoothly, or adapting to various display sizes, transformations are the fundamental tools that bring order and versatility to the world of digital design. So let's consider an example of transforming a point in a 2D space. So to transfer the point in a 2D space, first we need to translate the origin of xy to xy and then rotating x dash to x to align with the x-axis. As we can see in the picture over here, first we need to do a translation, then rotation along the x-axis, and the final result will be the r cross t, which will give us the correct point after transforming the coordinate system. Coming to 3D transformation. 3D transformation is the process of manipulating the view of a 3D object with respect to its original position by modifying its physical attributes through various methods of transformations like translation, scaling, rotation, and shear. 3D transformations play a crucial role in presenting and visualizing three-dimensional objects and scenes on a 2D space or other output devices like a gaming console or TV screen. So these transformations are fundamental for creating realistic and visually appealing 3D graphics. These transformations are often combined to achieve complex effects, and they play a crucial role in creating 3D graphics, animations, and simulations. So one of the 3D translation. So 3D translation is similar to 2D translation with extra coordinate, as it involves moving an object or a point in a three-dimensional space along one of the x, y, or z axis. This transformation is typically used to change the position of an object within a 3D scene. So it's nothing but the process of changing the relative location of a 3D object with respect to the original position by changing its coordinates. So as we can see in the picture over here, so after translating a point to the new position, to x dash, y dash, z dash, we can see the resultant matrix with tx, ty, tz, which are the translation distances for x, y, and z axis. And in mathematical notation, we can represent the new point as P cross P, where P is equal to XYZ and P dash equal to X dash Y dash Z dash, which is a new position of the object. Yeah. Now let's talk about 3D rotation. So in 3D rotation, it involves changing the orientation or angular position of an object or a point in 3D space. Rotations are used to manipulate objects, view them from different angles, and create complex 3D animations. So there are three kinds of rotations where we can rotate an object just parallel to a specific axis so that coordinate about which this object rotates remains unchanged, and the rest of the coordinates get changes. In total there are three kinds of rotations that are possible: rotation about the x-axis, rotation about the y-axis, and the rotation about the z-axis. Let's have a look at the rotation about x-axis. As you can see in the picture here, we are rotating an object around the x-axis. So we can, in mathematical perspective, we can extend the 2D rotation equations to 3D. As you can see below, x dash remains x as we are rotating an object around x-axis, and y dash equals to y cos theta minus z sin theta, and z dash equals to y sin theta plus z cos theta. In mathematical notation, matrix notation, we can represent it as the new position of object as the matrix as given here. Similarly, rotation about y-axis, we can see in the picture the object is rotated around y-axis, and similarly we can use the same 2D equations where x dash equals to z sin theta plus x cos theta, and y dash equal to y, and z dash equals to z cos theta minus x sin theta. In matrix representation, it can be represented as given in the picture here. Yeah, finally, the 3D rotation around z-axis. As we can see in the picture over here, we have rotated an object around z-axis. So similarly, we can extend the 2D rotation equations to 3D as well. So the x dash equals to x cos theta minus y sin theta, y dash equals to x sin theta plus y cos theta, and z dash equal to z. In matrix representation, it can be represented as in the picture here. And also, we can rotate an object around an arbitrary axis. So when the object is rotated about an axis that is not parallel to any one of the coordinate axes, then additional transformations are required. First, we need to align the object, and then the object is being back to its original position. We need to follow the few steps here. So to rotate an object around an arbitrary axis, first translate the object to the origin. As we can see in the first picture here, we need to translate this object to the origin in the step 1. In the next step, we need to rotate the object so that axis of object coincide with any one of the coordinate axes. After moving it to the origin, we need to make sure that it aligns with one of the coordinate axes, which can be either of x, y, or z. In the next step, we need to perform a rotation about coordinate axis with whom the coinciding is done. So now in the next step, we need to rotate an object around one of the axes where the object is parallel to the one of the axis. After rotation around the axis, we need to apply the inverse rotation to bring rotation back to the original position. And the next step, we need to bring the we need to apply the inverse rotation to bring the object to its original position. Then the final step, translate the rotation axis to its original position. There is also other way of rotating a 3D object using quaternions. Okay, the technique 3D rotation using quaternions is a powerful technique for performing smooth and efficient rotations in 3D space. Quaternions are a mathematical construct that avoids some of the complexities associated with other rotation representations. They provide a mathematically robust way to present and manipulate rotations, making them a popular choice in game development, 3D modeling, and other 3D applications. A quaternion represents two things. It has x, y, z components, which represents the axis about which the rotation will occur, and a term w, which represents the amount of rotation that occur about the axis. As we can see in the equation here, the quaternion is defined as q equals to w plus xi plus yj plus zk, where w, x, y, z, x, y, and z are real numbers, whereas I, j, k are imaginary numbers. Yeah. Coming to the, let's consider these two quaternions Q1 and Q2, which are defined as W1, X1, Y1, Z1, and W2, X2, Y2, Z2. So Q1 cross Q2 cross W will be the W1, W2 minus X1, X2 minus Y1, Y2 minus Z1, Z2. The important thing here to note down is that when Q1 cross Q2 is not equal to Q2 cross Q1, as quaternion multiplication is not cumulative. So in mathematical notation, we can represent a quaternion x, y, z, w as as m equals to the matrix given here.
Hello everyone. So today we are going to continue our presentation from my friend. So today in this presentation we'll be covering 3D scaling on an arbitrary point, 3D reflection, 3D shading, and transformation between 3D coordinate systems. And at last we're going to look at some 3D transformation examples. So let's begin. So first, we have matrix 3D scaling. So what does 3D scaling mean? So 3D scaling means nothing but whatever we have seen in the 2D scaling, but over here we are doing the same scaling in the 3-dimensional space where we have a new z-axis. So which means in simple terms, we are expanding matrix representation expands from 2D scaling to accommodate scaling in the 3 dimension. That's a simple explanation and seamless extension of these concepts and principles applied in 2D scaling to 3D scaling space. It is crucial for resizing and adjusting objects within a 3D environment accurately. That's very important because if that hasn't been done, then entire object shape will be changed. And next, so let us over here. I've represented matrix S. So it stands for scaling matrix that determines the scaling factors along x-axis, y-axis, and z-axis. Over here we can see which are defined by sx, sy, and sz. So and p dash represents the transformed point after the scaling in the 3D space. And P signifies the original point, P's position in 3D space, and the equation demonstrates the P's point's position changes after applying the 3D scaling transformation using the scaling matrix. So over here, we'll be using this matrix and we are going to multiply with x-axis, y-axis, and z coordinates based upon the scaling factor. Then it is like P equals S into P, S dot P. So here, as we can see, as you can see, there's a pyramid type of object where which is placed in XY coordinate space. So what you need to do is we need to take the P is the point where the original object is placed. Then we're gonna move that object to the origin. Then we'll be scaling based on the scaling factor. Again, we're gonna replace the object to the original point, which is P. That's how scaling would be performed. So certain graphic software may offer scaling capabilities exclusively concerning the coordinate origin. In such scenarios, the procedure involves the subsequent steps. So know the given point of the coordinate origin, implement the scaling transformation in relation to the coordinate origin using the designated scaling equation. And at last, return the point to its original position by applying the appropriate translation. So this would be the first, then we're gonna bring the object to the origin, then scaled according to scaling factor, and bring the object to its original position. Yeah. Now comes to the 3D reflection. So 3D reflection in computer graphics is used to reflect to objects like mirrors and shiny surfaces. Reflections may be an x-axis, y-axis, z-axis, and also in xy plane, yz plane, and even zx plane. The reflection relative to a given axis are equivalent to 180-degree rotations. So this is a sample example of 2D reflection. So over here we can see when there is an object on in this coordinate space, the reflection. So in this coordinate space, the reflected image would be have to present 180 degrees inwards to it. Same to XY plane and Y axis and even XY plane. Over here, this is a good example for 3D reflection. We have an object in ZX plane. So since it is in ZX plane, it has to reflect on inverse to its 180 degrees, which would be ZY plane. Over here, yeah, based upon the reflection side, we need to reflect. So yeah, this is the reflection is performed. And 3D sharing, sorry, oops. 3D sharing transformation. So basically 3D sharing involves modifying the shape and geometry of objects in 3D space, particularly variable for achieving realistic perspectives projections. What is perspective view? So perspective view refers to varying appearance of an object as observed from different directions and distances, and utilizing 3D sharing transformations to accurately represent how the object would appear in real world perspective view. So over here we have an example to draw a cube 3D on a screen 2D. Alter the values of x and y not are proportional to the distance from z reference. So this is how, yeah, there's a sample example. And in 3D sharing, suppose if you have to perform 3D sharing in yz with respect to x, so this is the matrix that we need to consider. And in zx with respect to y value, then sharing xz, then this would be the matrix. This is how the matrix is represented. Same goes with xy with respect to z, and sharing along z axis since we are sharing in the 3-dimensional space. So sh of shx comma shy multiplied by p is equals to p dash. So over here p is the original point of the object. These are the original points, and these are the shared matrix points. This is how once we multiply, we're gonna get the final destination point where we need to present object. When transitioning between coordinate system, it is assumed that it is assumed that just a moment, yeah, when transitioning between coordinate system, it assumed that a new x dash y dash z dash system is defined in relation to an existing xyz system. To map xyz coordinate descriptions to the x dash y dash z dash system, we begin with translation that aligns the x dash y dash z dash coordinate origin with xyz origin. Subsequently, a series of rotations are applied to align corresponding coordinate axes. If there are differences in coordinate intervals due to scaled variation in the two systems, a scaling transformation may also be required for compensation. The rotation for coordinate axis transformation can be constructed using unit axis vectors, transforming unit vectors u dash, v dash, and w dash on xyz axes respectively. Coordinate system transformation assumption is an assumption that x dash y dash z dash system defined relative to the xyz system. Coordinate mapping means transfer xyz coordinates description to x dash y dash and z dash system. Initiate with the translation align the coordinate origins x y z to x dash y dash z dash. Alignment of axes, a sequence of rotations align corresponding coordinate axes. Facilitates seamless translation between coordinate systems. Handling scale variation. If different scales are present in the coordinate systems, applying scaling transformation to compensate for interval differences. Rotation matrix for axis alignment. Utilize the unit axis vectors to construct the rotation matrix. Achieves transformation of unit vectors u dash, v dash, and w dash on the x, y, z axes respectively. So let us look at some 3D transformation examples. So over here, this is a 3D translation example of a translation, how we are translating three-dimensional object. And same goes with the rotation with respect to the origin. Over here, same with respect to an arbitrary point, rotation with respect to an arbitrary point. Yeah, again, one more scaling. So first we have an object, then this is the P, then we're gonna bring that point to the origin, then we're gonna scale, then we're gonna replace P with the original point, So these are the reflections, and this is the sharing with respect to the x-axis. So this is a translation of the chip object by 3, 2, -3. And same the rotation. Over here we have rotated 60 degrees. And scaling by factor of half and 3, as you can see over here. And reflection. So this is how the scaling is performed, as we have already discussed. These are in software examples translation. This translation, when we do translation in the software, the rotation in the software of a 3D cube, and when we scale the cube, this is how it comes. So thank you. So this is Team Benjamin. Thank you once again.